In this video, we're going to look at Newton's second law in terms of momentum. Now, we did Newton's second law in grade 11, but this time we're going to look at Newton's second law in terms of momentum. Now, this is what it states. It states that the net force acting on an object, is equal to the rate of change of momentum of the object in the direction of the net force. Okay, the net force acting on an object is equal to the rate of change of momentum. Here's the relationship here. So F net stands for the net force, or the resultant force, and then delta P is our change in momentum, and then delta T is the change in time. So what this basically tells us is this: if, let's say, we have an object which is moving to the right at a constant velocity, it's just moving at a constant velocity, then the momentum of that particular object will also be constant. But if the momentum of the object is to change, suppose, let's say, at some particular point it speeds up or it slows down or it turns, then the momentum is going to change. So if the speed of this particular object changes, suppose it's now 2v, then the momentum is going to change definitely, delta v, right? But for us to have a change in that momentum, for the speed of the object to either increase or decrease, or for its direction to change, there must be a net force that is acting on that particular object. So for the momentum of an object to change, there must be a net force that is acting on that object, which causes that particular object's momentum to change. You might recall Newton's first law of motion. In Newton's first law of motion, he says that an object will remain in its state of motion, either in a stationary position or moving at a constant speed, unless acted upon by a net force or a resultant force or an unbalanced force. So in Newton's second law, he talks about a situation where a net force actually acts on the object. So in the first law, there's no net force. But in the second law now, there is a net force acting on an object. But if a net force is acting on an object now, we expect that particular object to actually accelerate. Its speed can either increase or decrease. Okay. So in terms of momentum now, we say if the net force is acting on an object, then the rate of change of the momentum is actually equal to that particular net force. Okay. Now, we have some different situations here. If a net force or resultant force acts in the same direction as the motion of the object, then we expect the object to accelerate forward. So it's going to speed up. It's going to increase its speed. But if a net force acts in the opposite direction to which an object is moving, then the object will slow down. So we say it decelerates, or it reduces its speed. Or we can basically say it accelerates in the opposite direction. Okay. All right. Now, if a net force, okay, so this is the conclusion. A net force can actually cause the direction of an object to change. Number one, it can cause the speed of an object to increase. Number two, or decrease. Or it can cause both the object and both the speed and the direction of the object to change. So either way, the momentum of an object will change. Okay. So if a net force is acting on an object, the momentum of that object will change. And the momentum of an object can only change if there's a net force acting on that particular object. But you can have an instant where the net force is 0. If a net force is 0, then the object will remain stationary. So this is our Newton's first law. It will remain stationary or at rest, or it will keep moving in a straight line at a constant speed, or you can say at a constant velocity. The net force is 0 when there is no change in the momentum. So if our delta P is 0, then the net force is 0. Conversely, if a net force acts on an object, then the momentum of an object will change. So if no net force acting on an object, there's no change in momentum. If there is a net force acting on an object, there will be a change in the momentum. Thus, for the momentum to change, a net force is required. We need a net force in order to change the momentum of an object. So we have our expression here, our equation, F net equals to delta P over delta T. If this delta P is 0, right, or in other words, if the change in momentum is 0, right, it can only be 0 when the initial momentum is the same as the final momentum. If these two values here are the same, then we're going to have a 0 change in momentum. And if we divide by time, we'll also get a 0 net force. Okay, so that's what we're saying here. Then your object will remain at rest, or it will keep on moving at the same speed in a straight line. Okay. Right, another important point here to note is that F net is directly proportional to change in momentum. So we say the net force is directly proportional to the change in momentum. The bigger the change in the momentum, the bigger the net force. Okay. The bigger the net force acting on an object, the greater the change in momentum as well. Right. And then the net force is inversely proportional. To the change in time. Okay, so what this means is that if we have a bigger value of the delta T here, if this delta T is big, then the net force will be small. If the delta T is small, then the net force acting on the object will be bigger. Right, so these are very two important points that you need to understand from this relationship between net force and the rate of change of momentum. Okay, so we're going to make use of this expression in our later calculations, but you have to understand that net force is equal to the rate of change of momentum of an object.